which ticks at a definite rate. 1, 2, 3, 4, tick-tock, tick-tock. And I have another standard clock down here with which to compare it. Now, I look at this clock, and I compare it to this, and I'll discover that this clock seems to run fast. It's easy to see. Why? I mean, don't forget the thing is accelerating. So here's the picture in succession. Suppose that to make the clock very easy, it simply lets out a succession. Suppose that to make the clock very easy, it simply lets out a succession. Suppose that to make the clock very easy, it simply lets out a light flash. Pip, 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 pip. It lets out light flashes every second. Now I draw a picture of the elevator 1 second later. And here's the elevator 1 second later. So here a light pip came, and as he's coming out, I'm drawing this way because it takes some time for the light to get here, so as it comes down, the elevator's moving up. Now I draw a picture of the elevator at the next second. You say you're cheating, you made it go further. Yes, I'm not cheating. It's accelerating, isn't it? It's moving faster. And then in the next second, it's going still faster, so it's way up here. Now let's try to see how these signals will appear to approach the ground. There's nothing mysterious about it. You'll see that each time the signal has a shorter distance to go. And therefore, although they're emitted every second, since this one takes a long time, less time, they hit here with a smaller interval, smaller interval between them. Yes, because this one gets here quicker than this one got here, but they started a second apart, and therefore this comes more rapidly after this than it would have been before. So therefore, if you look at the clock with its pips, you'll see them more rapidly coming at the ground. Likewise, in reverse, the light from the bottom will approach the top end, and each time has to go further in an increasing sequence, and the times seem to be slower. So a man looking at the top, watching somebody up there, would see the clocks go fast, while the guy looking down the other way will see them go slowly. That's all right. There's nothing the matter with that, but this means that if every phenomenon inside the elevator is the same as it is in the gravity, this means that a clock, pip, 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 it lets out light flashes every second. Now I draw a picture of the elevator 1 second later. And here's the elevator 1 second later. So here a light pip came, and as he's coming out, I'm drawing this way because it takes some time for the light to get here, so as it comes down, the elevator's moving up. Now I draw a picture of the elevator at the next second. You say you're cheating, you made it go further. Yes, I'm not cheating. It's accelerating, isn't it? It's moving faster. And then in the next second, it's going still faster, so it's way up here. Now let's try to see how these signals will appear to approach the ground. There's nothing mysterious about it. That, but this means that if every phenomenon inside the elevator is the same as it is in the gravity, this means that a clock set at the top of the room, you make two standard clocks and put one at the top of the room and watch it, then it'll go faster. You say, yeah, but it's wrong. The time is the same, the distance is the same all the time. I know, but if you insist on the principle that Einstein insisted on, that you shouldn't be able to tell whether you're accelerating or you're in a gravity field, you've got to get the same phenomena, and he simply went ahead blindly but bravely and correctly, courageously but blindly, to propose that the thing would actually look like that. And now what was happening is that the time is different up here and then in here. That if you put an object here, it runs at a different rate. Even a standard clock appears to go slowly here when it goes fast here. This is the analog of a hot ruler that we were talking about. That we take the ruler to some other place and it just gets longer. We can't beat the game. And if we can't beat the game here, if you carry a clock up here, in this part of the world, time goes slower. That's all. Everything goes slower. Everything? Why everything? Suppose, how do you know human beings go slow or something like that? If we put two different kinds of clocks here, if they don't both look the same, well, they would look the same in this case. They look the same in that case. Well, anyway, they got to look the same. Or else you could find out something was the matter. Never mind. All things have to go the same. I can't get a quick argument on it. Otherwise, you would be able to see the difference between this case and this case. Now, there's a very peculiar idea that time varies, the rate of time or clocks or things varies from place to place. It's a difficult idea, but it's the idea that Einstein used, and it's one which turns out to be correct, believe it or not. In this thing, we can figure out that the apparent rate of the clock which is received, the apparent rate that we receive it, is not the same as the rate at which it's emitted, or the standard rate of emission, as we just mentioned, but differs. And if you figure it out in here, you see it comes out divided by 1 minus g, the acceleration, times h over c. There are several ways. You can sit down, because of shortage of time. It's an interesting moment, that shortage of time. Because of shortage of time, I won't explain the detail of it, but the idea is you can figure it out yourself by just counting how far the thing goes and how much decrease in time there is between the things, and get this formula out. A very easy way to get the formula is to use the Doppler effect and to notice the following: that the receiver of the light is always moving faster than the emitter. It's always moving toward the emitter. When the emitter was moving, it's moving at a low speed. When it's received, the receiver is moving at a fast speed. And the receiver is always moving toward the emitter by a velocity, which is the velocity which has been accumulated during the acceleration, during the time, h over c, that the light has gone from the top to the bottom. So this is the Doppler effect that corrects this formula. This is the Doppler effect for light from the top to the bottom. For those who like mathematics, you can also show that, well, that's good enough. Now, I would like to, since this is such an important idea, I would like to demonstrate it just still another way, that it's true by using other laws of physics, and it's interesting. We can prove it by the conservation of energy. Supposing that gravity acts on the total mass and the total energy content of a thing, and not just on the rest mass, and there are lots of experiments that demonstrate that, we can prove it by the conservation of energy. Suppose that I have an atom, which can be, or a nucleus or something, which can be in a low energy state, EO, and in a higher energy level, E1. And then it can emit light, a photon or a gamma ray or something, by going from E1, going from the excited state to the lower state, and the frequency of the gamma ray is related to the energy difference by this formula. That's standard stuff. Now, suppose that we start with a system in energy E1, so that its mass, as you know, is E1 over c squared. Then we carry that thing up to the top of the room. I carry this excited atom up, and I do a certain amount of work. Because the mass corresponds to E1 over c squared, the work is the mass times the gravity constant times the height. That's the work done in carrying it up. Now when it's up here in E1, I let it emit its photon, and so it turns to E0. Now I'm carrying it down again after it's emitted the photon. When I'm carrying it down, because it's emitted some energy and is not as heavy as it was before, the work I do is less. So in order, I would get perpetual motion if it weren't for the fact that the energy that the photon gives me down here is more. You see, or negative perpetual motion anyway. The idea is you do more work in carrying it up than you get back carrying it down, and to make the conservation of energy work out, that extra work appears in the energy of the photon. Another way to put it is that the energy of a mass up here is the gravitational energy plus its rest energy. Well, at any rate, if you add this extra work to the work of the to the work that you would ordinarily get from the photon, then you get GH over C times the difference of the work going up and down, and you see that the frequency observed must be different than the frequency that you would get if you didn't carry it to the ceiling, by the numerical factor 1 plus GH over C. This is a very small numerical factor, and experiments have been made to demonstrate the truth of it. There was a man standing here inside, and he let go of a ball. It'll fall to the ground. What? Well, sure. Well, your ball is there, and the spaceship moves up, and it leaves the ball behind. I mean, until it hits the floor. Yeah? The ball is left there, and the spaceship is accelerating, so it hits. The floor hits the ball. From the point of view of the man, the ball hits the floor. Same situation in here. All you fellows, for all we know, we're all on a spaceship, see, accelerating. And the reason that you feel the pressure on the seat of your pants is because you're being accelerated upward. In order to get accelerated upward, if I hold this up, you see, it proves the